Hi, Stuart here, and today we're going to continue our 12-factor talks, this time on disposability, number 9. Again, the base reference for this is the excellent Manifesto at 12factor.net. Disposability, the further the code moves to the right, the less time your code has to terminate cleanly. So if we're running on hardware or a virtual machine, if we have full control of our operating system, the shutdown can be managed. The shutdown can wait patiently for things to be done. If we move that same thing into a container or a function, that gets harder and harder, and the amount of grace time you have gets less and less. And one of the things that we see when customers rush to the cloud, and they try to go from virtual machine bases all the way up to functions, which is sort of the equivalent of trying to high jump to Mount Everest, is they don't do the modernization work required to tackle the disposability problem. And so the continuum is hardware, virtual machines, platform as a service, different kinds of hosting within there, containers, functions. And that is what we mean by moving right. The upshot of this is, if you have less and less time to terminate your process as you move right, then your code has more and more opportunity to be terminated in an unpleasant way, and the result to be loss of data and work. And that's not okay. Disposability also refers to, in part, processes starting up quickly, but generally speaking, slow starting processes fall into the more annoying category, especially if the other components in your system are willing to wait patiently for them to come into a ready state. They have some sort of retry mechanism, or they go to sleep for a little bit and then they try you later, right? They're good cloud citizens in that way. And we're going to talk about that in a different video. Again, the abrupt termination of your process while you're in the middle of processing something is something you have to think about as you move right, if you don't want to have loss of work and data. And generally speaking, you don't. There's lots of different definitions of unit of work, and Martin Fowler's PA of AA definition below is very kind of transactional and very much about clusters or groups of state entities. But I'm going to talk about disposability in the context of message processing. And in that context, a unit of work is the smallest distinct delivery of value, e.g. one step in a sequence of steps. So understand that units of work, that even the definition varies depending on what we're talking about. And I tend to be hyper-focused on message-oriented systems, so I feel like I'm qualified to say something about that and disposability. What makes a unit of work unstable? If your data gets processed multiple times in a harmful way. Just because the data got reprocessed doesn't mean that the end result is harmful, other than it probably wastes some computing cycles. But if, for example, I go up to update the same row in a table or the same graph in a NoSQL database, and the thing I update it with is the thing I updated it with before, well, no harm, no foul. It's at most irritating. Harmfully would be anything that would be a destructive operation. And in some cases, rather than do that, rather than allow updates and deletes, which theoretically, right, you could have a race condition, or you could have something completely unexpected. We tell people that maybe the journaling pattern is a better fit, and we have a video on that. Loss of workflow state, like the message flowing through the system has no idea what it should do next. That's not a great thing and should theoretically never happen. Work in limbo, lost work, where messages just don't get processed to some end. By the way, the dead letter queue or, the error state is a perfectly valid end result. because at least it didn't get lost. It ended up somewhere definitive. The definitive place it ended up was unhappy, but it ended up somewhere. And we have a nice video, by the way, on 6 problems in graph-oriented systems. You can go watch if you want to know more about that. The other problem is the inability to detect misconfiguration. So one of the few fatal errors that workflow systems should ever exhibit is if the workflow system itself can't run successfully because it's misconfigured. So if you are transforming a traditional big loop system, or you're transforming some sort of other kind of what I call tidal flow, where things are happening in groups and sets and mass, you have to be able to make sure that you are able to detect misconfiguration. The other thing is, the shorter the time you have, the shorter the grace period between the time some external force decides to kill your process and the time your process ends, as that gets shorter and shorter, you need to do things in smaller and smaller steps so that you have the opportunity to resume in a sane sort of way. You don't want to do anything that will extend the execution time of any one step, even if that means a slight decrease in efficiency, because you could do some awesome operation all in one go. But in fact, that makes the time of execution sufficiently long that that interval between the time that you're told you're shutting down and the time you lose state, you lose everything, right? Your process is gone, may not match up well, may not align well. And then workflow systems just generally shouldn't crash. If the configuration is bad, that's a legitimate reason to refuse to run, right? And that is a kind of crash, and that's probably the best kind, because you shouldn't run if you're unable to do useful work. By the way, that doesn't include transitory failures like this service or this database or this file system being temporarily unavailable. That's not a good reason to crash a process. That's a good reason to put work back into the waiting to be done pile and try again and keep doing that until you can do something useful. The rubric we have is your code shouldn't be a Jenga tower. As you break up these monoliths of processing, and I'm not talking about monolith applications. I'm talking about taking something that does everything all in one go and breaking into a set of distinct steps. As you take pieces out, you shouldn't be turning your code into a Jenga tower, where the removal of the wrong brick or the movement of something causes the whole thing to come down to a crashing. So units of work are typically, in my context, done as part of a workflow. And there are lots of different classifications of types of workflows, but for simplicity's sake, I've broken them down, and I think about them mentally as being in one of these patterns or some combination of these patterns. And they are a straight pipeline, right? We go from A to B, and if we have aberrant conditions, they get shunted off to the side. So you can think of web request response pipelines that way. You can think of hub and spoke patterns. So if you're using a topic queue, or you're using a finite state machine, or you're using BizTalk with a centralized message bus, then you have a hub and spoke pattern. That is, the state is in the center. And everything else devolves down to some sort of a graph of some kind. And they can be mediated by a queue or not. They can be mediated by intermediate storage or not. It doesn't really matter. The point is that it is hopefully, a directed graph and not an undirected graph. And each of these can have problems. And again, I refer you to the rubric about 6 different horrible things that can go wrong with graph systems. But the idea is that each one of the boxes, the green boxes, and in fact the terminal gray box, is a step in a workflow, and each step is a unit of work in the message processing context. So here's the key ideas behind what it takes to make workflows disposable. Idempotency. right? Each message that passes the system should have a unique ID that allows us to detect if something's been there before. Each step should be uniquely identifiable, either by itself, that is, that the step in question knows what step it is, which is often the case in finite state machine engines, or the message itself carries along with it its desired step target. What should happen to me next? Or we have built up some sort of routing system with mutually exclusive expressions. And that one requires just a tiny bit of explanation. So in the graph model, you can see we go from 1 to 2 or 3. And the choice about whether or not to go to 2 or to 3 should be mutually exclusive. And so typically in these systems, we're either using a finite state machine to make the decision. Oh, the value of this is this, therefore it goes to 3, otherwise it goes to 2. But in any case, whether it's a finite state machine or expression, the same message should always have exactly the same behavior. In other words, if it's going to go to 3, it should always go to 3. If it's going to go to 2, it should always go to 2. And you should try really hard not to break that. Now, obviously, if you add a 2b and turn 2 into 2a, then those 3 choices should be absolutely mutually exclusive of each other. And that's what we mean by a mutually exclusive expression. They should be reentrable. So if my message flows into my step can look at it and go, oh, I've already done that. I don't really need to do anything. I'm just going to pass you on to the next thing. Fine. And in fact, a lot of workflow systems work that way whether or not the message is going through for the first time or not. The processing step, the unit of work, looks at the state of the message and goes, oh, there's nothing for me to do about this. I'm just going to pass it on. So it checks the box. It says, I've done this. In some cases, checking that box is inferential. That is to say, in the case of a pipeline, I'm just going to fall through to the next thing. I'm not going to do anything, right? In other cases, like hub and spoke and GRASS systems, I'm going to make a state change to the message to cause it the next time it's rehydrated to go to a different processing step. Circuit detection is, have I been here before? By the way, that's not always bad. For example, I might come into a step and go, oh, wow, I'd love to process this, but I'm missing some data that I'm going to need. I'm going to send it down this enrichment workflow, and then when it shows back up, it'll have the extra data that I want, and I will be able to process this. So reentrability isn't a bad thing, but you need to do it with circuit detection. That is to say, you need to have some mutually exclusive expressions that allow you to say, I'm capable of processing this message or not. And if I am, that I have or have not processed this message before. And if I have processed this message before, do I ignore it or do I process it again? Because sometimes that's a good thing. But you have to have circuit detection that says, wow, this is the 5th time I've seen this message. That's not allowed. That's weird. It's odd. The state of the message has basically not changed since I last saw it. And again, you can use hashing and journaling to help you figure that out. And therefore, instead of, blithely reprocessing it or choosing to do nothing and just passing it on, I'm going to kick it sideways into some sort of exception workflow. And the exception workflow is going to be designed for, I've seen this message way too many times. So something went wrong. Go fix it. Hydration and dehydration is very important to disposability. Dehydration means that my process can write all of its relative state to somewhere when it dies, and when a new process starts up and wants something to do, we can pull that state back and work on it again. And queues are great for this, especially queues with leasing. And you can watch our video on good queue patterns to learn about leasing. But the idea is that in my workflow, I want the opportunity in between steps, if I'm told to shut down, to dehydrate where I was and to be able to resume where I left off. And lastly, we want to pull in this idea from Saga about compensation, that we've detected that something has gone wrong. And then we go, okay, well, what should I do? And usually what you should do is take that message and shunt it into the appropriate compensation workflow that says something has gone wrong, and then I want you to make it go and do the right thing. And so, for example, if we have a series of transactions flowing through our system about general ledger, what might happen in the compensation part of the workflow is that we might enter a backing out or compensating transaction to our journal that says, well, we weren't able to complete the entire flow of cash from A to B, or from this account to that account, or this system to that system. And so we want to put back the money we took out of this account. Other compensation mechanisms might be that we have taken a certain number of this item out of inventory, but it turns out it was unshippable. So technically, those things need to be returned to inventory. And so those are all different kinds of compensation, and there can be as many different kinds of compensation as there are types of workflows. But the idea is that you should have a compensation strategy. How do we break up monolithic things into units of work? And that is, we go through our monolith processing, and we start identifying the smallest units of work. Remember, the definition is something that delivers some sort of qualitative business value. And that's kind of a gray area. It's a judgment thing. But you also want to have to think about how long it takes that series of operations to complete, and is that inside the envelope of my termination interval? That is, the time between the time I'm told I'm going to die and I actually die. Figure out how to make each one of them reversible, reenterable, and if you can't do that, figure out a compensation. Break loops into sequences. So this would be one of the strategies for breaking loops into sequences is to take collections of things that you'd normally loop through and linearize them by putting them into queues or journals or stacks or some other system where more than one consumer can, in an idempotent way, take them off. And queue mediation, there's a lot on this channel about that. That's probably the default behavior. And then, of course, you should, create the workflow pattern, and you want to be really thoughtful about, do I have a pipeline? Do I have a hub and spoke? Do I have a graph? And if I have a graph or a hub and spoke, are the expressions mutually exclusive? And then I want to run a bunch of workloads through my new workflow, and I want to kill them or tell them they're going to die. And I want to test the losslessness, right? I want to make sure that if I start with 100 messages, that 100 messages end up in the terminal state. And remember that an exception is a perfectly valid terminal state, right? It ends up in the pile of unprocessable messages, or messages that need compensation, or messages that are malformed, but at least it ended up somewhere that it should. And if I run that experiment over and over and over and over and over again with the same messages with different interruptions, I should always get the same results. Right? Stopping and starting my workflow. If I have 100 messages and I do that experiment 20 times with random interruptions, I should always end up with the same result. So that's the test for functionality. And then lastly, do each of the workflow steps operate in the appropriate interval? And does the overall workflow have a reasonable processing time from end to end? There may be business drivers that govern that. And it may be that, in fact, instead of moving your workflow or your processing system to the right, in order to accommodate the performance requirements, you actually need to move it left so that the process has more time between the time it's told to quit and the time it dies. I want to have a sidebar about singletons, because singletons are the often unconsidered problem in trying to make something that has disposability, right? So in 12-factor, we just don't like singletons because we're unable to satisfy the concurrency rule that's part of 12-factor. That is, you should be able to scale out. But the other thing about that is that if you have a singleton, right, and it dies, then all the processing dies too. So they're bad disposability because, in theory, our workflow, unless the entire workflow is ordered to just stop for some reason, workflows should never die, right? The loss of a single node shouldn't result in the workflow stopping. And so if you have a singleton in your workflow, you have a single point of failure, and that's bad. And so, you try to make things have high availability, and you try to make sure that you have ways of instrumenting to make sure the parts of your workflow are alive and healthy, and that you have a log stream to look at your unit of work execution, your workflow execution. And you apply the how to get rid of my singleton strategy, which is this strategy. So the first thing and easiest thing to do, can it be load balance? Can it be clustered? Some workflow hosts, in fact, can be clustered. They have native clustering using Raft or some other algorithm. Can we burst the work into a queue? And then we can have multiple producers and multiple consumers. If we can't do that, can we put it into an electoral group? And we have a nice electoral group example in No Singletons. And if you can't do any of those four things, you need a refactor, because singletons are an anathema. And I'll point out that if you have something like a file system or an FTP server or whatever that you need to routinely scan to see if there are new units of work appearing, new messages in the form of files appearing, that you can put that process into an electoral group, right? And then only one is active at a time. But if one of them dies, the others will take over. So theoretically, there's only one process still running, but if that process dies, that part of the workflow won't die. And that's the point. My name's Stuart. Thank you for your kind attention.